Hello everybody, welcome. This is May 2023, paper 2, and it's from time zone 1. So here we have a 15-mark question. Let's read it. The depth of water, W meters, in a particular harbor can be modeled by the function Wt equals A cos Bt plus d, where t is the length of time in minutes after 6 in the morning. So a few things going on. What is this function? The function maps the depth of water at a particular time. So essentially, even when we're dealing with cosine or sine or trigonometric functions in general, we're still dealing with inputs and outputs in some kind of sense. That is to say, we input some value of t, and then we get some value of the depth of water at this instance. Continue on. On January 20th, the first high tide occurs at 6 in the morning, at which time the depth of the water is 18 meters. The following low tide occurs at 12:15, when the depth of water is 4 meters. This is shown in the diagram. So a few things going on here. They're telling us time. Time is measured in minutes. This is our input. And time measured in minutes after 6 in the morning. So even though if we were to put in some value of t is equal to 0, this is actually corresponding to a value of 6 in the morning. And that's probably going to be important later on in the question. They're also giving us a high tide, a maximum at this point at 6 in the morning, which again would correspond to t is equal to 0, I suppose. And they're telling us that's 18 meters. And they're also giving us a low tide, 12:15, which is 4 meters. So they're giving us a max and a min in this instance as well. Okay, so we've got some trig function, and it's going to map onto some real-world situation where at the very end we should be able to input some value of t and then find the depth of water at that point. And these 4 questions, A, B, C, D here, they're asking us to find the value of A, value of D, the period of the function in minutes, and then the value of B. And if we know all of those variables, A, B, and D, then we should be able to create some function that maps onto this real-world situation. All right, so let's go ahead. I'm going to give a brief kind of explanation of trigonometric functions in general, and then we'll work through this problem, what these values of A, B, and D actually mean. What makes this problem, I think, particularly challenging, or trigonometric functions in general, is that there is nothing in the formula booklet in which to appeal to or kind of rely on in some sense. That is to say, the formula for the amplitude, or this midline, or this value of b, which is called the frequency, or even the period, this is something that we, in some sense, have to commit to memory, but the positive thing is that you can use intuition to work through a lot of these things. All right, so let's go and just have a quick overview of trig functions. I'm going to draw a set of axes, and let's draw it for this instance of weight as a function of, the depth of the water as a function of time, and they're telling us it's A cos B of t plus d. And this is the same thing, like if we wanted to, we could write it in general as y is equal to A cos B of x plus d. In this instance, t is just our variable, and then the depth of water is just our y value, our output. So either case, we'll use w and t for this function itself. Okay, so we have 2 functions. We don't ever, in the IB, they'll always give us the function. They'll always tell us it's a cosine or a sine function. The only difference between the two, I'll make another quick graph up here. The only difference between a cosine and a sine function is that a cosine begins at its highest point and then sweeps through a full cycle, whereas, and then I'll just complete a little more than a cycle, a sine function starts at its midpoint and then it goes through a cycle. Oops. Let me just edit that just a little. Sine function will go through its midpoint first, and then it will go through a cycle. So sine function starts here, cosine function starts here. So this would be cos of x, and then this would be y is equal to sine x. And the IB will always give you the cosine or sine In this case, we're starting from our maximum, so we've got a cosine here. Okay, so now what are these values? What are these values of A, B, and D here? A, B, and D. A corresponds to the amplitude, and let's write that out here. A is the amplitude. And what the amplitude tests is if we've got some function. I'm going to write a general cosine function here. If we've got some function, so it starts at its max, it's a cosine function, and then it goes down, and then it goes up again, and then it completes one full cycle. So amplitude measures the distance that we are from the midline. So if this is our midline or our resting point, the average value, amplitude measures the distance from the midline to the highest point. And to find the amplitude, we can take the max, the maximum, I'm just actually going to write max, minus the minimum, and then we can divide by 2. So max minus min, if we want to find the distance from the highest point to the lowest point, we could take the maximum minus the minimum and then divide by 2. So if we imagine this is the maximum, we want to see the distance that we travel from the highest to the lowest point. This would of course give us 2a, but we don't want 2a, we just want a. So amplitude max minus min over 2, and that's what this value of a corresponds to. This value of d is the midline, or what we're shifting our function up or down by. So for example, if we didn't want our function to be at this midline right here, we could define a midline up here, for example, and then the midline of this function would be something like this, I suppose. So it would be shifted up, and that's exactly what our midline would do, and then it would go over. And so our midline would now rest something around here, I suppose, or maybe a little higher. This would be the value of the midline, or the center line. And if this midline is the point at which we rest at, or the center point, to find the value of d, which we'll call the midline, is just going to be max plus min over 2. Essentially the center line that you run through, or that our trig function runs through. So max plus min gives you the value of d. Maybe I'll write these out. So this is a, this is amplitude, this is d, this is the midline. And then later on, they asked for the period. The period is the time taken for one complete cycle. So I'm actually going to write that out. The period. The period is not something that's given to us again in the formula booklet. It's the time taken for one whole or one complete cycle. So to do this, we often need to look at the graph, or sometimes they'll give us some information. In this case, they actually do give us some information here. But oftentimes we would choose one point on the graph and then ask ourselves the question, when has this graph swept through, or when has this function swept through one complete cycle? And we see that, okay, it gets back to its max point right here, and then how long does this take? That would be our period, the time taken for one complete cycle. That would be the period. This last value, which is probably the most challenging to solve for, this value of b, this is called the frequency. And this is probably the more complicated one to solve. Our formula for frequency, or b, is equal to 360 divided by 360 divided by the period, the time taken to complete one cycle. Why is it 360 degrees? It has to do with what's called the unit circle. We won't go into depth on this, but it's potentially enough to know that we sweep through one whole circle in 360 degrees, and we're asking essentially how many periods fit into 360 degrees. And that will give us our value of b. So a, once again, our amplitude, the distance from the midline to the highest point. And how can we find that? Let's find that distance, the maximum minus the minimum, and then divide by 2. So max minus min, divide by 2. If you know the midline itself, sometimes you can find the midline first. That one might be the easiest one to find. That's just our kind of line that we rest at. So that would be max plus min over 2, or essentially the average, right? So here's the highest point, here's the lowest point. What's that midline? What's the line that goes right through the center? And then if you know the midline, if you find the midline, you can find the distance from the midline to the max, and that's exactly what the amplitude is as well. So you can reverse the process, find d, and then say, okay, well, if this is the midline, how much do we need to go up by or down by to get to our max from the midline, or to the min from the midline? That would also be another way to find it, the value of a, or the amplitude. Here they structure it a little differently, but if you can find d, then it's often easy to find a as well. Period is the time taken for one complete cycle once again. So how long does it take us to go from one point to another corresponding point, or how long do we complete a full cycle? And frequency, this has to do with the unit circle, which is maybe a little complex in terms of its theory potentially, but the question we're essentially asking is, how many cycles can we fit into 360 degrees? And this is going to give us the value of b. All right, so once again, none of this is in the formula booklet. None of these formulas are in the formula booklet. We kind of have to remember what they are. D, the midline. A, the distance from the midline to its maximum point. Period, time taken for one cycle. And then frequency, probably the most challenging of all, how many periods, how many cycles fit into 360 degrees. All right. So now that we've got that out of the way, I suppose, let's see if we can apply this to this question right here. All right, so they want us to find the value of a. I'm actually going to work it out in reverse order because I think that might actually be helpful. I'm going to find d first and then a. So d, we said, was the midline. Let's even maybe use the same colors here. So this was d, this was the midline, and that's d is equal to max plus min divided by 2. So in this case, maximum, they told us the water had its maximum depth at 18 and its low tide at 4 meters. So once again, max at 18, minimum at 4. So if we have our midline, that center line that we go through, the average, it's going to be 18 plus 4 over 2, or 22 over 2, or 11. And that would be our value of 2. So let's box that in and say d is equal to 11. Okay. So now, if we wanted to, I mean, like through intuition, we could find the value of amplitude in another way. So if we know the midline is equal to 11, maybe even draw it in here, I suppose. We can then ask ourselves the question, okay, well, if this is 18 and our midline is 11, then what distance do we need to go from, let's say, the midline to the highest point? Or similarly, if we know this is equal to 4 and our midline is at 11 right here, what distance do we need to travel? And once again, it's 7. So sometimes it is actually helpful to go from d and then to a, or d into a. Either way, let's work it out. We found the value of 7 just through intuition. This is a 2-mark question, so they are expecting some process. You could probably write, and I imagine you could write 11 plus what is equal to 18, or 18 minus 11, and this would give you 7. But let's use our formula right here for amplitude. That's what a is. Amplitude. A is equal to max minus min. So the distance from the peak to the trough, the highest point to the lowest point, divide by 2. And now we have 18 minus 4 over 2, or 14 over 2. And this gives us a value of 7. So we know that a is equal to 7 here. Okay, the period of the function. Let's ask ourselves the question, okay, how long does it take to go through one complete cycle? This one's actually a little more challenging. We can see it's even 3 marks. So there's going to be some extra kind of computation involved, something extra in terms of the process. So let's ask ourselves the question. Going to need a little more space. I'm going to write it up here. The period, the time taken to go from one complete cycle. So we know we have a high tide, which occurs at 6 in the morning. So right here, this is 6 in the morning. Here it is as well, 6 in the morning. And then all the way here, we have our low tide. And I'm going to erase some of this, I suppose. All right, all the way here, we have our low tide, which it's hard to tell on the graph, and that's probably purposeful, I suppose. Low tide occurs at 12:15, and here it's in minutes, so we're going to need to do some conversion. But we know a max, we know when it occurs, and we know where the min occurs. And when we go from a max to a min, you can ask yourself, okay, well, how many cycles have we gone through? If we've gone from the max to the min, we've gone through half a cycle, and we're going to need to go from the min to the max again, and that's going to be one other half cycle. So essentially what we have here, I hope this isn't too kind of lengthy, but we have this instance where we know, let's say I'm going to draw a standard function. We know we've gone from our max to our min, and now the question is, okay, well, if we know that this itself is one half cycle, it's going to be another half cycle until we go one full cycle. So let's ask that question. So from 6 to 12:15, how many minutes have passed, or how much time has passed? So let's see the distance. This is going to be a little funny. I think it's actually best to use intuition. If you started at 6 in the morning and then you go all the way to 12:15, how many hours pass? Well, if you start at 6 and you go to 12:15, we have 6 hours and 15 minutes. 16 hours and 15 minutes. But of course, the function won't really take hours and minutes, two different kinds of units. T itself is just in terms of minutes, and that's what they're asking us to find the period. They're asking us to find the period in terms of minutes. So 6 hours, we know there's 60 minutes in an hour, so this is going to be 60 times, 6 times 60. So 6 times 60 is going to be 360 minutes. I'm going to write that out. 360 minutes. Let's just write 360. And then we also have this 15 minutes right here. So what do we know? We know we go through a half cycle in 360 plus 15. 360 plus 15 is going to equal 375. So we go through a half cycle in 375 minutes. Let me just make sure that's all correct. 6 hours plus 15. 6 times 60 is 360 plus 15, 375. Okay, so half cycle in 375. How much is a full cycle? We'll just multiply by 2. Multiply by 2. And 375 times 2 will give us 750 minutes. Okay, so once again, from 6 in the morning to 12:15, we go 6 hours and 15 minutes. 6 hours, there's 60 minutes in every single hour. 6 times 6, 36, plus this 15 minutes. 375 minutes to go a half cycle, therefore a full cycle is 750. So let's say the period is equal to 750 minutes. So the calculations themselves, we can see they're not like super challenging themselves. Essentially it's really knowing where to find the information, max and min, max plus min over 2, and these kind of things. Period, time taken for a full cycle. But this is otherwise somewhat of a challenging question, at least to get started in some sense. So find the value of b. B itself is the frequency. B is, let's use the same color once again, the formula for b is equal to 360 over the period. This is probably the trickiest one to remember. So 360 over the time taken for one complete cycle, 750, and I'm going to work that out and we'll get a decimal of 0.48. Okay, so we know that b is equal to 0.48. Really, once you become familiar with this, this is a great 9 marks. And once you're familiar with trig functions, and they do often have a real similar kind of structure, especially when the graph is given to you, that potentially it's a good way to maximize results and so. Okay, so now we know a, b, and d, so we know everything there is about this function, and we should be able to map onto this situation. Usually after this they ask us to apply it. Now that we've got the function, let's do something with it. Okay, so what do we have here? Naomi is sailing to the harbor on the morning of 20th of January. Boats can enter or leave the harbor only when the depth of water is at least 6 meters. Find the latest time before 12 to the nearest minute that Naomi can enter the harbor. Okay, so let's work this out. We're going to need to graph this one. Let's go ahead and, running out of space a little, but let's write out our function itself. So we have y is equal to a cos b of t plus d. A we found out was 7. 7 cos b we said was 0.48, t plus, and then the midline again was equal to 11. So this is our function, 7 cos 0.48 t plus 11. And if we put that into the calculator, we should be able to graphically see what's going on here. Okay, so she's sailing into the harbor on the 20th of January, that's the day. Boats can enter or leave the harbor only when the depth of water is at least 6 meters. So only when the depth of water is at least 6 meters. So let's erase this and let's see what this means. So this function tracks the depth of water through time. Boats can enter the harbor only when the depth is at least 6 meters. So this is 6 meters right here. This is our W, right? W is equal to 6. That's our output essentially. W is equal to 6. And where can she enter the harbor? Well, she can enter the harbor here and here and here. The depth is at least 6, right? At least 6. It's above this line, right? But after this time rather, now the water is less than 6 meters. So she can no longer go into the harbor. So really, what we would like to do is find the point at which the water goes from being above 6 meters to now below 6 meters. That's going to be the last time she can enter into the harbor. Okay, so let's go ahead and look at the calculator here. Here we go. So just bring a new window up. Make sure you're in degrees when you are graphing this as well. Sometimes there's a difference between the calculator window and the graphing window itself. So make sure that this is in degrees. Otherwise you'll get some, well, you're getting correct results. 7 cos 0.48x plus 11. So the calculator only takes x's, of course. All right. And for trig functions, these can potentially be a little difficult to find the window of. Zoom fit won't work too well. This is definitely not a quadratic or anything like that. And if we zoom out, it won't give us all that great of an idea of what's going on. So when we're working with trig functions, I recommend you go to the window settings and get some custom windows. And this is x min, x max, minimum x max x values, and then min max for y. So what do we know? We know that we're starting off when t is equal to 0, so let's put in maybe like t is equal to 10, for example. max. We want to make sure we get at least one full cycle. We know a cycle is 750, so let's do 1,000 minutes. Scale is auto, that's fine. Y min, so the lowest point, the lowest depth was 4. Let's put 0 in just to get some buffer. We could even put -2 or something like that. And then the max depth was 18 meters. Let's put maybe 24. Let's actually put -2 just to get some buffer. Sometimes it's easier if you have a little cushion on either side. So from -10 minutes to 1,000 minutes, and then from a depth of -2 to 24. This will give us one full cycle, and it's much easier to work with now. Okay, so there's our function. Let's ask the question, when is this function equal to, or when is the depth of water equal to 6 meters? So there we go. So here's depth of water on the y-axis, time, and here's the depth of water through time. The question is, when is the depth equal to 6? So menu, analyze graph. Let's find the intersection. And here we go, 282.47. All right, so after 282 minutes and 47th of a minute, not 47 seconds, but 47th of a minute, that's when the water first becomes, reaches a depth of 6 meters, and then it's going to fall below that. Okay, so let's go ahead and go back to the document for a sec. I'm going to clear up some space here. Just get rid of this, and then we'll write in here. Okay, and I think I'm going to get rid of this actually as well. I don't think we need this anymore. Okay, so what do we know? We know that this point right here is equal to 282.47, 282 minutes and 47th of a minute, and that's when we're at 6. This is our W or our Y value. We're at a depth of 6, and this is T, of course. Find the last time before 12 to the nearest minute that Naomi can enter the harbor. In this case, the last time before 12 to the nearest minute that Naomi can enter the harbor. Alright, so remember 12 o'clock would be 6 hours later, or 360 minutes later. This is 12 o'clock. The last time before 12 o'clock is right here. So, 282 minutes. 282 minutes. Yeah, I think we would of course have to round down, even if it was 200 and let's say 82.8 minutes or something like that. If the IB wanted to trick you, we would still need to round down to 282, because at 283 minutes, it's now below 6 meters. So find the latest time before 12 to the nearest minute that Naomi can enter the harbor. 282 minutes. And let's actually show some process. Essentially, we would put 6, that's our output for the depth. 6 is equal to, and then our function. We want to know when is 6 equal to 7 cos 0.48 t plus 11. There it is. Plus 11. Essentially, we're asking for what value of t is the depth equal to 6. You might be wondering, yeah, can you n-solve this? Potentially. In this case, you actually would be able to, but sometimes with n-solve, graphing is better visual. Sometimes for trig functions in general, you might have a value that's after. Maybe that's the one we're looking for. Or n-solve might give you something to the left, which won't be relevant. Graphing is going to be the easiest, I think. And then, of course, our answer is 282.47, or 282 minutes to the nearest minute. Alright. Find the length of time in minutes between 6 in the morning and 3 o'clock on 20th of January, during which Naomi cannot enter or leave the harbor. So the length of time in minutes between 6 and 15 where she cannot enter or leave the harbor. So let's convert these to time first, just to get a better idea. This corresponds to t is equal to 0. And here, the distance from 6 to 15 is going to be 9 hours. So 9 hours times 60 minutes. You can put that in the calculator. that's going to correspond to a value of 540. So when t is equal to 540. And really, that doesn't seem too bad of a question. So when can she not enter or leave the harbor? Here she can enter or leave the harbor. Here she can enter or leave, as long as it's above 6. But from here to here, she cannot enter or leave. So we know one value. We know after 282 minutes, she cannot enter or leave. And then if we find this other value, then we'll find out the total time in which she cannot enter or leave. So this is her no entry, essentially. This is where you can't enter or leave. Water's too low. So not a bad 2-mark question. Let's go back to the calculator and find the other intersection point, essentially. Analyze graph, intersection, and we see that it is 467.53. So the total length of time, and we want to put this in minutes once again. So let's go ahead and find out, actually sorry, let's go back to the calculator. We know the first time in which she can't enter, and the distance between these 2 points is going to be the total length of time she can't enter. After this, it's okay to go in and out. So going back to the document for a sec, at 467.53 minus 282.47. So between these times she cannot enter. So what is the total length of time between these 2 points? I'm going to work this out on the calculator that I have beside me. 467.53 minus 282.47. And this is 185 minutes. And what is this? This is a 6/100th of a minute. So find the length of time in minutes between 6 and 15 hours where she cannot enter. Okay, last little bit, let's round this down to 185 minutes. And then let's let's convert this to, actually it's already in minutes, we don't need to convert it to anything. So that's it. That one wasn't too bad, actually. A 2-mark question. I don't know why this one was so challenging of a 4-mark question. But, okay. Find the latest time before 12 to the nearest minute that Naomi cannot enter the harbor. I see what they're asking now. Okay. So sometimes it's very rare, I mean it's not often the case that the IB will make a mistake. Very, very rare things will be overly generous. When you see this 4 marks, it's possible to think of, okay, if you imagine the mark scheme itself, what are the steps that they're looking for? Here we need to graph it, of course. We need to set it equal to some value, and then we need to round this down to minutes. But they're asking for the latest time, not the total time that has passed. So 282 minutes. So just to go back to E here, this is all good right here, but E we need to do a little more work on. 282 minutes have passed. We know 6 in the morning is where we start, right here. So in a real world context, it wouldn't be enough to tell Naomi, for example, 282 minutes later, after 6, that's when you can't enter the harbor anymore. It would be more relevant in a real world context to tell what time exactly, what specific time. So in this case, we have to convert these minutes into hours and then find out the time, the latest time in which she can no longer enter. And that's something, to be honest, at first read that I myself missed. But 4 marks, that is a good indication. Okay, so 282 minutes. Let's divide this by 60 minutes. We know there are 60 minutes in 1 hour, so let's find out how many hours. I'm going to go ahead and do this on the calculator that I have beside me. and it's going to give us 4.7. So it's going to give us 4.7 hours. But that's not quite enough. That's, if we write this as 4.7 hours, it's 4 hours, and this 0.7 corresponds to 7/10, right? And 7/10 of an hour. Or let's just write 0.7 hours. 4 hours plus 0.7 hours. And how many total hours after 6 in the morning is this? 0.7 hours. 4 hours can stay as it is, but 0.7 hours in minutes we would need to multiply by 60, for example. And so 0.7 times 60 would give us 42. So what do we have? We have 4 hours, and then 0.7 hours, or 7/10 of an hour. 0.7 times 60, 60 minutes in an hour gives us 42 minutes. So 4 hours and 42 minutes. If we start at 6 in the morning, and we go 4 hours and 42 minutes, 6 hours plus 4 hours gives us 10, and then 10:42. That would be the latest time that Naomi can enter. Sorry about that, I had missed that on first read. So depth of water, find the intersection point. It occurs at 282 minutes, but we're asked for the latest time before 12. And so 282 minutes, how many hours does that correspond to? Divide by 60. It corresponds to 4.7 hours. 4.7 hours is 4 hours and, well, 0.7 hours. 0.7 hours is, again, we don't want hours, we want it in, let's say, this minutes, not 70 minutes or anything like that. 7/10 of an hour, 42 minutes. 4 hours, 42 minutes, and then add that on to our starting value. So 6 plus 4 is 10, and then 42 minutes after. So 10:42. All right. Pretty good question overall. Apologies for the, not exactly the misread, but the oversight, I suppose. All right, everybody. I hope that was helpful, and as always, best of luck. Take care.